Good morning, everyone. What a great day for thesis presentations. My name is Michael Coppi, and today I am so excited that my thesis partner, Andrew Mullan, and I are presenting our thesis entitled An Improved Design for an Oscillating Water Column Wave Energy Converter. Our principal advisor is Professor Martin. I would like to first thank our principal advisor, Professor Martin, for his insights, his years of dedication to the MEC team, and most importantly, his unbridled optimism. I would like to thank our reader, Professor Onus, and our editor, Professor Harris, for their valuable assistance in communicating our thesis document. I would like to thank Professor Royce, Pat Doherty, and Jamie Swan for their assistance with the building and testing of our design. I would like to thank Frank Biskup from Voigt Group for his assistance with identifying valuable testing parameters. Additionally, I would like to thank the Department of Energy for our research and SNAP grant and the WebMech team for their enthusiasm and support. In today's presentation, I will first go over the really interesting history and background. Then, I will identify the objective of this thesis. Next, I will discuss the theory, design, and construction of our testing apparatus. Andrew will then present on our testing procedure, our results and conclusions, and recommendations for future work. As early as 1799, Pierre-Simon Girard was conducting work on harnessing the vast potential of ocean waves. After noticing the oscillatory motions of ships moored in a harbor, he attached a lever to a ship and was able to power a sawmill ashore. In the 1970s, international political turmoil resulted in a dramatic increase in the cost of petroleum products. Today, this period is known as the oil crisis, and as a result of this, nations without fossil fuel resources, especially in Western Europe, began research into renewable energy. Most recently, growing concerns over climate change have led to an increase in demand for consistent renewable energy production. One major source of renewable energy is wave energy. Oscillating water columns, or OWCs, are shoreside wave energy converters. OWCs harness wave energy with a chamber, a turbine, and a power takeoff mechanism. The first step in the process is when the water column rises and falls due to incident waves. As the water column rises and falls, an air column is consequently expanded and compressed. Finally, the resulting bidirectional airflow is directed across a turbine that spins a power takeoff mechanism. Here is a rendering of an oscillating water column. As you can see, as the incident waves enter the chamber, the water column rises and falls. Consequently, this compresses and decompresses an air column, which drives the turbine. I'd like to thank Ian Kirkpatrick for rendering this awesome video. There have been several significant oscillating water column installations. The Pico power plant was opened in Azores, Portugal in 1999. Unfortunately, inadequate structural design led to system flooding and turbine malfunction. In 2000, the Limpet power plant was opened in Islay, Scotland. It was designed by Voigt Hydro and had a rated power of 250 kilowatts. Lastly, the Motrico wave plant was opened in 2011 in Spain. It was also designed by Voigt Hydro and had a rated power of 300 kilowatts. Andrew and I consulted with the lead designer of the Limpet and Motrico plants in order to improve our system's design. Our thesis continues the work of Sasha Kritzuk and Juliet Lehman's thesis in 2022, which focused on the design, build, and test of an oscillating water column. The primary focus of their thesis was to set up a wave energy converter for testing at Webb. The work of Halder et al. Outlines methods to improve system efficiency by improving the turbine's design. Lastly, Gayatri et al.'s paper details the effect of chamber shape on system performance. These findings were then applied to our thesis to improve Kritzuk and Lehman's system, where Andrew and I have focused on improving the power output. Thus, the objective of this thesis is to design, build, and test an oscillating water column wave energy converter with an improved power output. The first major component of the system is the chamber. The primary function of the chamber is to seal the water column, allowing it to drive the motion of an air column. This behavior is similar to the cylinder of a diesel engine, which seals the piston and allows air to be compressed and expanded. The two main parameters that affect the system are the shape and the size. With a larger volume of air displaced over each wave cycle, there is increased flow over the turbine blades. The size can be changed by changing the dimension of the chamber and by changing the angle of the walls. The shape of the chamber can affect its resonance characteristics, as well as dynamically accelerating the flow with a nozzle-like effect. The main working principle of the turbine is that it takes fluid kinetic energy and converts it to rotative mechanical energy, which can later be transformed by a power takeoff mechanism. As with any energy transfer process, there are inherent losses. So a major goal of this thesis is to maximize the efficiency of this energy transfer. A unique feature of this device is that the working fluid of the turbine is the air, not the water. Finally, due to the cyclic nature of the waves, the turbine must be able to handle bidirectional airflow and rectify it into unidirectional rotation. What I'm essentially saying is that a unique turbine is needed, one that must spin in one direction regardless of the direction of airflow. Our thesis analyzed making changes to a Wells turbine, which is a bidirectional turbine. The blades sit at zero incidence to the plane of rotation. As incoming flow arrives at the turbine, it splits at the point of maximum thickness along the foil. A low pressure region and a high pressure region are created, which begins rotation. So, as the blade increases in velocity, the relative angle of incoming flow decreases, which is a reduction in the angle of attack. Here is a further explanation of the forces acting on a Wells turbine. First, the blade velocity causes a relative velocity of the flow. This is the angle of attack for the foil, and an increase in blade velocity decreases this angle. Flow over the blades generates lift and drag, which act in opposing directions tangentially. The tangential force can be found by subtracting the drag component from the lift component, and this is the force that causes the turbine to rotate. The axial force is from the combined axial components of lift and drag. This is a load on the turbine, and it does not contribute to rotation. The first turbine parameter examined was blade sweep, which is like the rake of a propeller. Sweep has been shown to delay flow separation and improve the effects of compressibility. Sweep improves the system's operating profile at the expense of its peak performance. The blades can be swept towards the leading edge, known as forward sweep, or towards the trailing edge, which is known as reverse or backward sweep. Another factor is the number of stages. These stages are simply the rows of blades, as seen in a two-stage and three-stage turbine on the right. By having more stages, more energy can be extracted from the flow. However, increasing the number of stages can increase cost and complexity, while efficiency improvements may diminish. The blade number is the number of blades per stage. This number is usually odd to reduce the effects of vibrations and fatigue. A stage with more blades can capture more energy and increase the consistency of rotation. Similar to stage number, the number of blades is also a trade-off, with more blades increasing cost, complexity, and weight. Lastly, an end plate is an appendage that encompasses the outmost extents of the blades. This is done to minimize flow leakage and three-dimensional foil effects. In doing so, this can reduce vortex shedding and increase efficiency. However, the end plate can increase drag in some conditions and further complicate the turbine's design. The power takeoff mechanism converts rotational mechanical energy into another form. For example, the turbine shaft can be used to power the rotor of an AC electrical generator, and this power can be supplied to a power grid for other applications. The design and construction can be divided into several different design phases: the turbine housing and assembly, the proof of concept apparatus, and our final wave chamber. We designed several turbines to evaluate turbine parameters. First, we used the Kritzook-Leben turbine as a control for testing. This turbine was their best and final turbine after iteration. All of our turbines use the same hub dimensions and foil characteristics. Our first turbine used uniform sweep, meaning the blades are evenly spaced and swept in both directions. Our second and third turbines use linear sweep, with the second turbine's blade swept forward and the third's swept in reverse. The fourth and fifth turbines evaluated the effect of curving the blade sweep, with the fourth having curved forward sweep and the fifth having curved reverse sweep. Lastly, in turbine 6, we evaluated the effect of adding a third stage, while in turbine 7, we evaluated the effect of adding a ring-type end cap. The first step in our construction process was assembling the turbines. The turbines were 3D printed in 6 pieces and glued together while aligned on the output shaft. The housing and assembly was adapted from Kritzuk and Lehman's design and can be seen right here in front of Mark. The design consists of an acrylic tube, a 3D printed assembly, and two rolling element bearings to reduce friction. The turbine shaft is then coupled to the generator shaft to create electricity. The chamber was constructed from half-inch acrylic panels. The top panel has a circular cutout where the turbine housing is placed. To allow the front wall to rotate, a piano hinge supports the front wall, which is then locked in place using pins. I would now like to invite up my most trusted friend and thesis partner, Andrew Mullan, to discuss our testing methodology.
Thank you, Michael. Now that Michael has thoroughly walked you through the theory, design, and construction of our main testing apparatus, I will be discussing the testing procedures and the results from testing. The proof of concept testing was broken into two phases. Phase 1 had a focus on rapid turbine design iterations of the major parameters at an early stage of the project. Phase 2 focused on minor modifications to the turbine's mass, inertia, and blade area. At the conclusion of Phase 2, 3 turbines were picked to move on to the final phases of testing. The final testing was also broken into 2 phases. Phase 3 focused on down selecting from 3 turbine designs to 1, while Phase 4 focused on analyzing the effect of the chamber wall angle on the overall system performance. Phase 1 testing was designed to be done outside of the Robinson model basin with a portable chamber. A plywood box was constructed with a piston and an orifice to mount the turbine. This piston was manually actuated at a frequency of about 0.625 hertz, or about 37.5 beats per minute. This frequency was chosen because it was easy to manually replicate, as well as close to a frequency that would ultimately be used in final testing in the Robinson model basin. This benchtop method allowed us to rapidly test a number of turbines in succession and look for relative improvements in performance. The following video demonstrates an exciting operation of the benchtop testing rig, although at a much higher frequency than we would ultimately test at. You'll have to look closely at the beginning, since that is when you can actually see the turbine spinning. Note that the turbine is not coupled to the generator at this phase of testing. From Phase 1 testing, 3 turbines were selected to move on to Phase 2. The first of these turbines was Kritzuk and Lehman's turbine from their 2022 thesis. This turbine was 2 stages with no sweep and would serve as a baseline for comparison. The second turbine selected to move forward was a 3-stage turbine with no sweep. This turbine was selected because of the apparent performance improvements seen with the additional turbine stage. The final turbine selected to move forward was a 3-stage turbine with curved reverse sweep. This turbine had the highest average RPMs in proof of concept testing, and when compared to the other turbines, would allow us to isolate the effects of sweep and stage number on overall system performance. Notably, the blade number was constant across all turbines tested, and the end cap turbine proved to perform worse than expected. It's likely that, at this small scale, the additional drag and surface deformities canceled out any potential advantage that the end plate could provide. The Phase 2 testing was conducted in the Robinson model basin. The selected turbines from Phase 1 were slightly modified with changes to their mass, inertia, and blade area. These turbines were tested in the condition expected to provide peak power output, which is a wave amplitude of 0.035 meters and a frequency of 0.4 hertz. The old chamber from Kritzuk and Lehman's thesis was used, and performance improvements were analyzed by tracking the mean and maximum number of RPMs of the turbines. The turbines were coupled to an unloaded generator at this phase of testing. The video I'm about to play shows some testing from Phase 2. You'll be able to see incident waves causing the turbine to start spinning. In the final testing phases, more precise data measurements were necessary. One of the 2 main measurements taken was the power output of the oscillating water column. The model generator's leads were wired across a 56.4 ohm resistor on a breadboard. A MIDAC multimeter was also wired across the same resistor, and the voltage across this resistor was measured at a sample rate of 1000 Hz. Since power is equal to the voltage squared divided by the resistance, the power output was easily calculated. The second measurement that was necessary during the final testing phases was the angular velocity of the turbine. To achieve this, a tachometer was set up to record the RPMs of the turbine. The remote optical laser sensor was mounted to an 80-20 aluminum assembly. The laser pointed at a piece of reflective tape on the turbine generator coupling, and as the turbine spun, the tachometer recorded the RPMs of the turbine at a sample rate of 1 Hz. The image shown depicts the final testing setup used in both phase 3 and 4 of testing. At the bottom of the image, the acrylic chamber can be seen sealing the top of the Robinson model basin, along with the angled forward wall that was rotated in phase 4 testing. The turbine and turbine housing are shown at the center of the image, mounted in the orifice. The tachometer and laser sensor are shown just aft of the turbine housing, pointing at the coupling. Finally, the MIDAC and breadboard are shown above the turbine on the Robinson model basin carriage wired to the generator. Air gaps in the chamber were sealed with duct tape, and weights were placed all over the top to reduce flexing and leakage. As mentioned earlier, 3 turbines were selected to be tested in phase 3. The new chamber was installed for this testing phase as well. Each turbine was tested at wave amplitudes of 0.025, 0.03, and 0.035 meters, as well as frequencies of 0.4, 0.6, and 0.8 Hz. These ranges were selected because they encapsulated the upper range of waves that could be produced in the Robinson model basin without spilling out of the tank, as well as the lower end of what waves could be produced and make any power output at all. The chamber angle was held constant at 0 degrees for the entirety of phase 3. The first set of results from phase 3 testing highlights the differences amongst the 3 turbines. Each graph displays power output in milliwatts on the y-axis, plotted against the time of turbine operation in seconds on the x-axis. The top left graph is for the 3-stage no-sweep turbine. The top right graph is for the 2-stage no-sweep turbine. And the bottom graph is for the 3-stage curved reverse sweep turbine. All graphs are for a wave amplitude of 0.035 meters and a frequency of 0.4 Hz. The solid red line on each graph indicates the maximum power output, and the dashed dot blue line on each graph indicates the mean power output. From these results, we can see that in the peak wave conditions tested, the 3-stage no-sweep turbine had the best performance with a power output of 62.7 milliwatts. The second set of results from phase 3 testing highlights the differences in performance at different wave frequencies. Once again, each graph displays the power output in milliwatts on the y-axis, plotted against the time of turbine operation in seconds on the x-axis. Both graphs shown are for the 2-stage no-sweep turbine. The left graph for a wave amplitude of 0.035 meters and a frequency of 0.4 Hz. The right graph for a wave amplitude of 0.035 meters and a frequency of 0.6 Hz. A graph for a frequency of 0.8 Hz is not shown because this condition did not produce any power output at all. The solid red line on each graph again indicates the maximum power output, while the dashed dot blue line on each graph indicates the mean power output. From these results, we can see that wave frequency plays a major role in the system's performance, with lower frequencies corresponding with better performance. This makes sense, since changes in wave frequency can push the system in and out of resonance, and the 0.4 Hz waves crests and troughs were visibly the closest to the length of the chamber. The final set of results from phase 3 testing highlights the differences in performance at different wave amplitudes. The graph shown displays mean turbine speed in RPMs on the y-axis, plotted against the wave amplitude in meters on the x-axis. For all data points, the wave frequency is 0.4 Hz. The dotted black line corresponds to the 3-stage no-sweep turbine. The solid red line corresponds to the two-stage no-sweep turbine, and the dashed blue line corresponds to the three-stage curved reverse sweep turbine. Interestingly, although the three-stage turbine with no sweep had the peak power output, it was the three-stage turbine with sweep that had the most consistent power output. This was shown at different wave amplitudes, meaning that it had an increased performance envelope at the expense of power performance, peak power performance, which aligns well with the theory. From phase 3 testing, it was clear that the additional stage in the Wells turbine was beneficial to system performance. Additionally, sweep proved to be effective at increasing the performance envelope, but with a major reduction in peak performance. We decided that the increase in performance envelope was not worth this reduction, and so we selected the three-stage no-sweep turbine to move on to phase 4 of testing. Now for phase 4, I promise it's the last one. With the turbines down selected to the three-stage no-sweep turbine, it was time to test the effect of varied chamber wall angles. To test the maximum condition with the chamber still remaining sealed, we tested wall angles of -30, 0, and +30 degrees. This was once again done at wave amplitudes of 0.025, 0.03, and 0.035 meters, as well as frequencies of 0.4, 0.6, and 0.8 hertz. The figure on the left shows the completed testing matrix for mean power outputs, and the figure on the right shows the completed testing matrix for maximum power outputs. A key takeaway here is that the 0-degree chamber angle always produced greater outputs than either -30 or +30 degrees. Additionally, the 0.8 hertz condition still showed an inability to get past its startup torque threshold. The final set of results from phase 4 testing highlights the differences in performance at different wave amplitudes for the three chamber angles tested. The graph shown displays mean power in milliwatts on the y-axis, plotted against the wave amplitude in meters on the x-axis. For all data points, the wave frequency is 0.4 hertz. The dotted black line corresponds to the 0-degree wall condition. The solid red line corresponds to the +30-degree wall condition, and the dashed blue line corresponds to the -30-degree wall condition. From this graph, it is then clear that of the three wall angles tested, the vertical wall at 0 degrees had the best system performance. However, it's important to note that it is possible that an angle between 0 and +30 degrees produces better results by balancing the increase in chamber volume, the increased chamber length, and the decreased forward wall depth for a net power gain. Before I get into the conclusions, I just want to touch on some challenges that were faced in the build and test portion of this thesis. One of the biggest challenges faced was the alignment of the turbine and generator shaft in the coupling. If these were misaligned, which they sometimes were, there was a side force on the generator shaft that would cause it to catch and not spin. To get around this, we carefully aligned one bearing at the base of the turbine housing and another one at the top to firmly hold the shaft in place. We then cut the excess shaft as short as possible to minimize the potential to bend out of plane before reaching the coupling. Another major challenge was the torque of the generator. Because it was just a hobby DC motor wired in reverse, there was significant torque that was sometimes too high for the Wells turbine to overcome. Indeed, one fellow researcher on Amazon recently claimed in June 2024 that it would need a hurricane to work. Now, I don't know if I go that far, but it is true that a DC generator with less torque or some sort of AC generator might produce better results. The third major challenge was energy losses in the chamber during testing itself. The massive amounts of air pressure were causing the top of the half-inch thick acrylic chamber to flex significantly. Additionally, air would try to find the path of least resistance and blow out of any exposed crevices. To combat this, we placed over 100 pounds of weights on top of the chamber, duct taped all gaps and exposed edges, and plugged holes to try and create an airtight seal. The final challenge was based on limitations to the wave testing capability in the Robinson model basin. As mentioned earlier, a wave with amplitude of 0.035 meters and a frequency of 0.4 hertz was near the upper limit of what could be tested without the water spilling out. The trends indicated that had we gone higher in wave amplitude and lower in wave frequency, we might have been able to see better results. There were four main conclusions at the end of this thesis project. The first was that in our setup, three-stage Wells turbines have greater power output than two-stage Wells turbines. The second was that sweep will improve the power envelope, but at the expense of peak performance. The third was that the front wall angle definitively changes the system's resonance characteristics. However, further testing is necessary to determine the precise effects. Finally, the fourth conclusion was that the wave frequency dominates over the wave amplitude in affecting the system's performance. For any follow-on projects, we have four major recommendations for future work. The first is to conduct further testing on chamber shapes, including front wall depth, front wall angle, and chamber volume. In our current setup, the front wall angle can easily be tested at more angles up to 45 degrees in either direction, assuming that the chamber can remain sealed. However, the front wall depth and chamber volume change with this, and the variables are not separated for clear analysis. A future thesis could design a chamber to isolate each of these variables to determine their effect on overall system performance. The second recommendation is to perform a CFD analysis of chamber resonance, which is currently done by the major companies designing oscillating water columns. The third recommendation is to investigate the feasibility of an offshore wave energy converter, which might be better suited for testing in the Robinson Model Basin. Finally, the fourth recommendation is to develop a more efficient power takeoff mechanism that does not limit the system in the same way that the DC generator does. Thank you for listening to our thesis presentation. I'd now like to invite Michael, Thomas, and Eli back up to answer any questions that you may have.